Hi, welcome to the Olympiad geometry. Let's continue our study on the 9-point circle. Here is a problem. Show that 9-point circle is tangent to inscribed circle and side tangent circle. So this problem is actually asking us to figure out the relation between circles, right? In the proof of that two circles are tangent, for example, if they are tangent inward, so let's say this is R, this is R, the distance of the center is D. So we can just prove that D equals to R minus R to prove that these two circles are tangent, right? And for another case, we can just prove this is R, this is R, this is D. D equals to R plus R, right? So basically, we want to find the distance from the 9-point circle center to the inscribed circle center. We want to find the distance. And for the inscribed circle center, we actually did a lot of calculation before in the chapter that we talk about the Stewart's theorem, which means here we also need to use the Stewart's theorem a lot. So this will be a very long video because we want to review all of them. Let's just review the Stewart's theorem first. The Stewart's theorem is saying that in a triangle ABC, P is any point on the BC, then we know that AP squared equals to AB squared times PC to BC plus AC squared times BP to BC minus BP times PC, right? In some case, we can rewrite this as AB squared times PC to BC plus AC squared times BP to BC minus BC squared times BP to BC times PC to BC, right? That's the Stewart's theorem. And if you recall the problems that we solved before, we actually find the circumcircle center O, the distance from circle center O to the inscribed circle center I, that OI squared equals to 2R squared minus 2RR, where R is radius of the circumcircle, and this R represents for the radius of the inscribed circle. No worries, let's just prove this again. So basically, we find the general solution or general expression that on the plane, right? Let me just draw it here. This is A, B, C. We have the inscribed circle center I. All right, how to get this inscribed circle center I? We just find the intersection point of angle bisectors, right? Angle bisector lines. So this equals to this one, this equals to this one, this equals to this one. So we want to find any point P to I, right? So we want to find the PI in a function of AP, BP, CP, and of course the edge BC. So that's A, AC would be B, AB would be C, right? A, B, C. We want to find this function. Okay, let's just draw the circle first. Right, that's a circle, and we have A, B, C here. I think this is a circle O, and we want to find that's inscribed center I. So let's say we have a point P here, right? P is here. We know AP, we know BP, we know CP, and we want to find the PI, right? We want to find PI. We want to find the PI. The first thing we can do is that we extend BI. Here, right? We extend BI to intersect AC on D. Right, so for here, because we already know the distance of, let me connect it. We're assuming that we know AP, we know BP, we know CP. So because we know AP, we know PC, we can figure out the length of PD. Right, once we get the length of PD, we know the length of BP, then we can use Stewart's theorem to find the PI. I hope that is not very difficult to understand. So we extend the BI. BI is the angle bisector of angle ABC, right? Intersect AC on D. So here is A, this is C, this is B. So we know that AD equals 2, because, let's say this way, because BD is the angle bisector of angle ABC, so we have AB to BC equals to AD to DC, right? So AD equals to C to C plus A times B, right? And DC equals to A to C plus A times B. Right, this should be very straightforward. Then we know the PC, we know the AP, we know the ratio of AD to AC, right? AC is B, right? So AD to AC, that is C to C plus A. DC to AC is A to C plus A, right? So we know all these ratios. So we should be able to calculate that PD square, right? Use the Stewart theorem. PD square equals to AP square times DC to AC, right? Plus PC square times AD to AC minus AD times DC. So it equals to AP square times DC to AC, that's A to A plus C plus PC square times AD to AC, right? This is AC, AD to AC, that's C to A plus C minus AD times DC, so that is B square AC to A plus C. Right? That is PD. We find the PD. And now we want to find PI square, right? Let's write it here. That PI square equals 2 PB square times PB square times ID to BD plus PD square times BI to BD and minus, let's see, BD square times BI to BD times ID to BD, right? So we want to find the ratio of BI to BD, ID to BD, and we also want to find the BD square. Right, BD square, BD can be, to find the BD square, we can still use the Stewart theorem in the triangle ABC, right? So BD square equals to AB square times DC to AC plus BC square times AD to AC minus AD times DC, right? It equals to AB square, that is C square times DC to AC, DC to AC, so it's A to A plus C plus BC square, that's A square times AD to AC, that is C to A plus C minus AD times DC, that is B square AC to A plus C, right? So it equals to, see here, we can extract AC out, right? So here we have C to A plus C, here we have A to A plus C, and then add them together, that is AC, right? So AC minus this one. So yeah, B square AC to A plus C, so equals to AC 1 minus, here should be this one, sorry, let me, right, this is correct. I forgot the square, right? If we multiply AD to DC, we have A plus C square here, A plus C square. So AC times 1 minus B square to A plus C square. Right, you may wonder why I can find this so quickly, just because this is unit list, so this number should be unit list. We have B square here, so the bottom should be square something, right? So it should be A plus C square. Yeah, that's a way. Actually, we introduced it before that we can easily find the one term is correct or not by using by checking the unit, right? Okay, so we got BD square here, right? BD square here, and we also want to find BI to BD and ID to BD. Remember that I is the inscribed center, which means that AI is the angle bisector of angle BAC, right? So ID to BD, see, ID to BI equals to AD to AB, right? So ID to BD equals to AD to AD plus AB, right? That equals to AD is BC to A plus C to BC to A plus C plus AB, AB is C, right? So it equals to BC to BC plus C, A plus C, right? So it equals to B to, see here, we can cancel all the C out, A plus B plus C. That is ID to BD. And we can calculate for BI to BD in the similar way. BI to BD equals to AB to AB plus AD equals to AB is C, right? So C to C plus AD. AD is BC to A plus C. So it equals to C A plus C to C A plus C plus BC. So it equals to A plus C to A plus B plus C. Of course, you can use 1 minus this to get this one. That's the thing. Okay, now we get the relation of ID BD. That's the ratio of ID BD. We got it. We got the ratio of BI to BD, and we have the BD square. So we can put all of them into this equation to get the PI square, right? So PI square equals to PB square times ID to BD. ID to BD, that is B to A plus B plus C plus PD square. Where is PD square? It's here, right? So it's AP square times A to A plus C plus PC square times C to A plus C minus B square AC to A plus C square, right? That is PD square times BI to BD. BI to BD is here, A plus C to A plus B plus C, right? So let me, so that's just a BD square, PD square times BI to BD, and we still have this term. This term would be minus BD square. This is BD square, right? This is BD square. That is AC 1 minus B square to A plus C square. That is BD square times this one, BI to BD and ID to BD. So that is B A plus C to A plus B plus C square, right? So this one equals to PB square B to A plus B plus C plus, see here, A plus C cancel A plus C, right? We have A left here, and that's A to A plus B plus C. So PA square times A to A plus B plus C. For this term, A plus C cancel A plus C, we have C to A plus B plus C. So we have PC square times C to A plus B plus C, right? And we minus this term, which is A plus C cancel one of the A plus C. So on the top, that is B square AC. On the bottom, it's A plus C, A plus B plus C, right? And then we want to have this one, which is minus. The first one is AC times all of this, so that is ABC, A plus C, to A plus B plus C square, right? And for the second term, it's actually a plus sign, right? So make it plus sign, and we have B to the power 3 times AC times, right, B to the power 3 times AC times A plus C to these terms. So that is A plus C square times A plus B plus C square. Right, so for here, it's very straightforward to look at, which is 1 to A plus B plus C times PA squared times A plus PB squared times B plus PC squared times C, right? And the rest part, let's deal with it separately, right? I hope you can see it here. Yeah. So we can simply just change this term as this way. We have, let me write it, start from here. So minus B squared AC times A plus B plus C divided by a plus c times a plus b plus c squared, right? Minus abc times a plus c squared times, that's it, right? Times a. We just times a plus c on the top and bottom at the same time, and plus. For this one, a plus c just cancel this a plus c square, one of this, right? So we got b to the power 3 ac, that's all. Right, and let's simplify this one. A equals 2, see here, b to the power 3 ac, here b to the power 3 ac. So these two terms cancel each other. In here we just left a plus c, right? And here we have another a plus c here, so which means this term becomes minus a plus c times b squared ac plus abc times a plus c. Right? So abc times a plus c. This one is abc times b, right? So it equals 2 minus a plus c times abc times a plus b plus c. Right? So comparing this one to this one, a plus c can cancel a plus c, a plus b plus c can cancel one of the a plus b plus c here. So eventually we got for this term equals 2 minus abc to a plus b plus c. Right? So we can simplify it again to a plus b plus 1 over a plus b plus c times pa squared a plus pb squared b plus pc squared c minus abc. Right? That is a general equation to find the pi square. Right? So for the oi square, because OA is radius of the circumcircle, OB is the radius of circumcircle, OC is radius of circumcircle, so R square, right, times a plus b plus c, and cancel with this 1 over a plus b plus c. So we got R square minus abc to a plus b plus c. Right. So if we look at the area of a triangle, and this one is an inscribed circle, right? The area of the triangle as ABC equals to half of a plus b plus c times r, right? Because we can simply, this is a times r times 0.5, that's the area of this triangle plus this triangle plus this triangle. So eventually looks like this, right? And it equals to half of, for example, a b c here and b c here, right? That is b times c times the sine a, right? And what is sine a? This is O, this is A, B, C. This angle equals to this angle, right? So sine A equals to sine BO, let's say it's D, BOD, right? This is 90 degrees. So sine BOD is BD to BO. BD is half of A, so A equals to half of BC times half of A to R, right? So we cancel this half out. Then we got, we put the a plus b plus c on the right, and we put the 2r on the left. So we got 2R equals 2. A, B, C to A plus B plus C. Right? That means OI squared can be rewritten as R squared minus 2RR. Right? Okay, we just get OI squared. Now we look at the author center. A, B, C. This is D. So center is here. This is O. This is H. This is E. Right? So we want to find, see here, we want to use this equation, right? We want to use that pi squared equals to this one. Right here, the P point would be the author center H. So we need to find what is HA, what is HB, what is HC, right? What is HA here? We want to find the HA square, HB square, HC square. Right? Well, that's the thing we're looking for. We can just connect BO and extend it to a point. Let's call it N, right? And connect NC. Because BN is a diameter, so we know that angle BCN is 90 degrees. Right, which means AD is in parallel with NC. AD is in parallel with NC. And we extend AD. Intersect the circumcircle on point, says Q. Right? Because AQ is in parallel with NC, so arc AC equals to arc NQ. Right? AC and NQ, they're equal. Which means if we connect AN here, we connect HC here. If we look at the angle CHQ or CHD, right? Let's connect ED as well. Angle CHD equals to angle CED. Why? Because angle HEC is 90 degree, angle HDC is 90 degree, so HECD is a cyclic quadrilateral, which means that angle CHD equals to angle CED, right? Angle CHD equals to angle CED. It is important. And angle, see here, because angle AEB equals to angle ADB equals to 90 degree, so AEDB is a cyclic quadrilateral as well, which means that angle CED equals to angle ABD or ABC, right? Equals to angle ABD. So CHD equals to ABD. And we know that angle ABD, that's actually equals to angle ABC, right? Exactly the same angle. Angle ABC reference to the arc AC, right? It should be equal to the angle reference to the arc NQ, which is angle QAN. So it equals to angle QAN. right? So we get angle CHD equals to angle QAN, which means AN is in parallel with CH, right? So AH is in parallel with NC, AN is in parallel with CH. We got that ANCH is a parallelogram, right? So we know that AH equals to CN equals to BN square minus BC square equals to 4R square minus A square. Oh, here, right? AH square equals to CN square equals to BN square minus BC square, right? This one equals to this one just because it's a parallelogram. And how can we calculate for NC square? That's because BCN is a right triangle, so BN square minus BC square. BN is a diameter of the circumcircle, so BN square, that's 2R square, which is 4R square, right? 2R square, which is 4R square. And BC is A, so it's 4R square minus A square, right? That's AH square. And just look at the form of this, we can easily get that BH square equals to 4R square minus B square, and CH square equals to 4R square minus C square, right? Now we just use the equation we already get, that PI square equals to 1 to A plus B plus C times PA square times A plus PB square times B plus PC square times C minus ABC, right? So we got HI square equals to 1 to A plus B plus C times PA square. What is PA square? That is P here represent for H, right? So HA square, which is 4R square times minus A square times A plus 4R square minus B square times B plus 4R square minus C square times C minus ABC, right? It equals to, see here, we extract 4 square out, then we have A plus B plus C, it cancel with this A plus B plus C, so we have 4R square here, and we have A to the power 3, B to the power 3, C to the power 3, minus ABC to A plus B plus C, right? So we have minus 1 to A plus B plus C, and here would be A to the power 3, B to the power 3, C to the power 3, plus ABC, right? That's HI square. Okay, what's the point to calculate this? You may ask. We're looking for that 9-point circle is tangent to inscribed circle. So we want to find the center of the 9-point circle to the center of inscribed circle, which is I here, right? We usually represent the center of 9-point circle to be V, right? So what is V? We already proved that. For example, this is O, this is H. We already proved that V is a midpoint of OH, right? O represent for the center of circumcircle, H represent for the author center. V is a 9-point circle center, right? V is a midpoint of OH. And if we have I here, we know the OI square, right? OI square equals to 4R square minus, OI square equals to R square minus 2RR. We already know the OI square. We know the HI square, which we calculated as here. And we know the ratio of VH to OH. we know the ratio, that's half, right? And also VO to OH, that's half. And if we know OH square, we can directly calculate VI square, right? That's the distance we're looking for. So the next term is that we want to find OH square, right? So let's come back to here, to this figure. We want to find OH square. See, OH square can be found with using Stewart's theorem in the triangle BHN. Right. So we need to find the HN square. HN square is actually very easy to find. Why? Because we already have the AH square, we have the HC square, and we know AHCN is a parallelogram, which means H to here, this point, let's call, AC intersect HN, let's call it on the point, for example, M, right? Because AHCN is a parallelogram, so the diagonal AC and diagonal HN intersects on point M, and M is a midpoint of HN, right? So we already know AH, we already know HC, and we know M is a midpoint, we know AC, we can calculate for HM square. For the HN square would be 4 times of HM square, right? So let's write HM square equals 2 half of, I'll just directly use the variant of the Stewart's theorem, right? That's the midpoint, right? So half of AH square plus half of CH square minus quarter of AC square. So it equals 2 half of, what is AH square? We have it here, right? 4R square minus A square. What is CH square? That's 4R square minus C square. And what is the AC square? AC square, that's B square. So quarter of B square, right? It equals 2 4R square minus half of A square, half of C square, and a quarter of B square. Right, that's HM square. And we know that HN square equals 2. 4 times of HM square equals 2. $16, right? 4 times of this, so 16 R square minus 2 A square minus 2C square minus B square, right? That is HN square. Now, if we want to calculate, we already have the HN square, right? We want to calculate for the OH square. So let me write it here. So OH square equals 2. Because O is a midpoint of BN, so OH square equals 2. Half of BH square plus half of HN square minus quarter of BN square, right? Equals 2 half of, what is BH square? That's 4R square minus B square, and half of HN square. HN square is here, right? Half of it, so that is 8R square minus A square minus C square minus half of B square, right? And we want to minus quarter of BN square. BN is diameter, which is a 4r squared, right? Quarter of 8, that is r squared, right? So this equals 2. See, this is 2r squared plus 8r squared, that's 10r squared minus r squared, that is 9r squared. And this is a half of b squared, and this is minus half of b squared. So 9 squared minus a squared minus b squared minus c squared. So, right, that's OH squared we find. Okay, now we look at this one. VI squared equals 2. V is a midpoint of OH, right? So VI squared equals 2, half of OI squared plus half of HI squared minus quarter of OH squared, right? It equals 2. What is OI squared again? That's R squared minus 2RR, right? So half of R squared minus 2RR plus half of HI squared, right? HI squared is this one, it's lengthy, but just write it down here. 4r squared minus 1 to a plus b plus c times a to the power 3, b to the power 3, c to the power 3 plus abc, right? And minus 1/4 of OH squared. What is OH squared? We find it here. So that is 9r squared minus a squared plus b squared plus c squared. Okay, now let's just simplify this. Here we have a half square, we have half r squared, we have 2r squared, we have minus 924r squared, right? So minus 924, this is this one is actually 8r squared to 4, right? So we have minus 124r squared, right? And we have half of r squared here, minus 124r squared, that says 124r squared, and minus here it is r, right? And then we calculate the rest part. For the rest part, we have let me write it this way. We have minus 2a plus b plus c times this one, a squared, a to the power 3, b to the power 3, c to the power 3 plus abc, right? And actually minus this one plus this one, so minus that's fine, sorry, this one here, and plus a squared plus b squared plus c squared, right? So it equals to 124r squared minus r, and we use this one and this one together, so that is plus 124 a squared b squared c squared times a plus b plus c 2, so a plus b plus c, right? That is this one, and minus twice of a to the power 3, b to the power 3, c to the power 3 plus a, b, c, right? That's what we got here, and then we extend this one. Let's extend this one. For the top part, that actually is minus, let's write this way, yeah, minus, see here, a to the power 3 minus 2a to the power 3, so minus a to the power 3, and similarly minus b to the power 3 minus c to the power 3, and we have a squared times b plus c, so plus a squared times b plus c, and plus b squared times a plus c plus c squared times a plus b. Right, c squared times a plus b, and then we do minus twice of a, b, c. Right, so for here, if we do it forward proof, it's kind of difficult, but let's do a reverse proof. Look at this one. Look at this one. We want to find the vi squared, but what is eventually we want to do? We want to prove that vi squared equals 2. We want to prove that the circumcircle, the 9-point circle is tangent to the inscribed circle, right? What's the radius of the 9-point circle? That's half of the circumcircle, right? Which is half r, right? And what is the radius of the inscribed circle? That's r. We want to prove this, right? It equals 2. Plus r squared, right? So basically, we just need to prove that r squared equals to this one. Right. Let me rewrite it. So we want to prove r squared equals 2. One by 4 times all of these, right? So r squared equals 2, 1 by 4, a plus b plus c, and on top of it is, let me check again. Yeah, this a squared plus b squared plus c squared times a plus b plus c minus twice of a to the power 3 plus b to the power 3 plus c to the power 3 plus abc. Right, we want to prove this. How? Remember that r equals to triangle area ABC 2. So a plus b plus c times r equals to triangle area, right? So twice of this divided by a plus b plus c, right? Which means r squared equals to 4 times of the square of the triangle area ABC 2, a plus b plus c squared. Right? And we can use Heron's theorem that the triangle area can be calculated as p minus a, p minus b, p minus c, where p equals to half of a plus b plus c, right? That means as the area square ABC equals to p minus a, p minus b, p minus c equals to half a plus b plus c times half a plus b minus c I'll just write, yeah, half minus a plus b plus c, half a minus b plus c, right? This one, and can be rewritten as 1 to 16 a plus b plus c, a plus b minus c, a minus b plus c, minus a plus b plus c, right? That's s squared. So we use this one times 4 divided by this one. We got 124 times a plus b plus c times a plus b minus c, a minus b plus c, minus a plus b plus c, right? That is 4s squared, and then 2a plus b plus c squared, right? A equals 2, 1, 2, 4, a plus b plus c, and on top of it would be a plus b minus c, a minus b plus c, and minus a plus b plus c, right? Look at these two. We just need to prove that a squared plus b squared plus c squared times a plus b plus c minus 2 a to the power 3, b to the power 3, c to the power 3, a, b, c equals 2. A plus b minus c, a minus b plus c, and minus a plus b plus c, right? This, we don't know. We just want to prove this one. So we extend the left part, that would be, see, again, this is a to the power 3 minus twice of the a to the power 3, so we have 1 left, so minus a to the power 3 minus b to the power 3 minus c to the power 3, and then we have plus b squared, a plus c plus a squared, b plus c squared, a plus b, and minus twice of a, b, c. That's the left side, right? And for this one, look at a minus a here, which means for the a squared, we have minus a to the power 3, right? And b minus b here, so we have minus b to the power 3. Similarly, we have minus c here, that's minus c, minus c to the power 3. And then for a square term, we have a here, right? And we have b plus c, right? So we have a here, we have b plus c. Maybe that is a little difficult to think of. Let's see if we have a better solution here. Yeah, if we can just extend this one. Okay, let's do brute force calculation. This one times this one equals to a squared minus ab plus ac plus, right, minus ab plus ac plus ab, that's ab, and minus b squared and plus bc minus ac plus bc plus, no, minus c squared times minus a plus b plus c, right? So here ab cancel this ab out, ac cancel this ac out. The rest part would be a squared minus b squared plus bc twice minus c squared, right? And minus a plus b plus c, so it equals 2. minus a squared and plus a squared b plus a squared c, right? Plus a squared b plus a squared c plus ab squared, right? This is ab squared and minus b to the power 3 and minus b squared c. This is minus, and for this one, we minus twice of a, b, c, right? And for here, plus twice of b squared c, and plus twice of bc squared, right? And then we have minus ac squared. Oh, that's plus, right? Plus ac squared minus bc squared and minus c to the power 3. It equals to minus a to the power 3 minus b to the power 3 minus c to the power 3. And for the a squared term, right, we have plus a squared. So we have this one out, this one out, this one out. A squared term, a squared, b plus c. So this one out. And for the b squared term, we have b squared a minus b squared c plus 2b squared c. That's a b squared c, right? So this out, this out, this out. Plus b squared a plus c plus for c squared term, we have 2bc squared. This is minus bc squared, so that's 1bc squared. And we have ac squared, so plus c squared a plus b. And then this out, this out, this out. We just have minus twice of a, b, c. Now look at this one and this one. They are equal, right? Which means we just prove that vi squared equals to this one equals to half of r minus r squared, right? We just prove this. So this one means that 9-point circle is tangent to inscribed circle, right? Okay, that's just half of the work. And we still need to prove that 9-point circle is tangent to the side tangent circle. What is side tangent circle here? Side tangent circle is something like this, right? I'll just so think about that. How do we find the center of the side tangent circle? We have A, B, C here. We want to find the center of the side tangent circle. We find the angle bisector of, because the distance from the center to the distance from the center to AB to AC to BC would be the same, right? Which means it should be on the angle bisector of this angle and on the angle bisector of this angle, and of course on the angle bisector of BAC, right? So these three lines are the angle bisector. So let's call it IA, right? It's IA here. So the question is that can we find another form of equation that on the plane we find any arbitrary point P, right? Can we just find PIA square as what we find in the PI square as well, right? That's a question. So So assume that AIA across BC on D, right? Let's just just draw it without A, B, C, I, A, and this point is D, right? We want to find the general equation of the PIA square, right? Because later on we can use the OIA square and the HIA square. Similarly, we use the same way we find the VIA square and prove that a VIA square, because obviously that's if the 9-point circle is tangent to the side tangent circle, then they are tangent outside, right? So we just need to find the radius of this tangent circle, and also we need to find the radius of the 9-point circle. We prove that we find the distance from the center to center, right? Same way, same method. We just need to find this. So let's try here. The first thing we want to find is that, look at here, this angle equals to this angle, right? So if we want to calculate the ratio of triangle, the area ratio of the triangle BIAD to triangle BIAA, it equals to half times BIA BD times sine angle IABD, right? BIA times BD times sine angle IABD, right? And for the area of BIAA, that's half of BIA times BA times sine angle IABA, right? It equals to BD times sine angle IABD to BA times sine angle sine IABA. That's a sine IAB whatever. Let's call it T, right? Sine IABT. And we know that IABT equals to IABD. So these two cancel each other, so equals to BD to BA, right? And we already know that the area of this one to this one equals to IAD to AIA. So IAD to AIA equals to BD to BA, right? IAD to AIA equals to BD to BA. That's a lemma we would use. And now we want to find, because we have this lemma, then we know the relation of DIA and AIA, right? Now we want to find that if we know PA, we know PB, we know PC, how can we find the PIA, right? Similarly, we have to use Stewart's theorem. So let me actually draw it here, right? So we have PB, we know PB, we know PA, we know PC. We want to find the PIA. right? That's what we are looking for.